Hello everyone, Alvin Isufi and myself, Inat Lagendijk, welcome you to the Essentials of Signal Processing lecture number 1. We hope that you have all signed up for the Mattermost channel of this course and that you have downloaded the Jupyter Notebook files from Brightspace, because these files also contain the theory exercises belonging to this week's lecture. In this first lecture we basically talk about what signals are, where we as computer scientists could encounter signals and signal processing, and how we approach teaching of signal processing to you, computer science students, namely via the combination of theory, exercises and practical software implementations. I find it important to stress that signal processing is rooted in quite a bit of mathematics, but that those mathematics are a means to an end. If you know the equations but have no idea what they mean and what the relevance is for computer science, then you entirely miss the point of this course. For that reason, turning the mathematical expressions into code, running that code, visualizing and understanding the results is an important part of this course. The learning objectives for this week are the following. First, you should be able to explain why digital signal processing is important. Second, given the description in words of how a signal is manipulated by a signal processing system, you can write down the input-output relation as a mathematical equation. Third, you can write down a signal given as an array of values in the form of a mathematical sum of weighted unit impulses, and vice versa, of course. Fourth, as a special case, you can write down the equation of a time-discrete sinusoidal wave signal and understand what the effect is of changing the values of the amplitude, the digital frequency and the phase. And finally, you understand how simple input-output relations work and what their mathematical notations are. The two important cases are delays and linear combinations. These two simple operations are essentially the basis for nearly all input-output relations that we're going to consider in this course, such as finite impulse response filters or FIR filters. I'm not going to discuss why signal processing is important at any length in this summary. Examples are all around us. Even the fact that you are watching this video is due to signal processing algorithms. Cameras and microphones digitize my visual appearance and voice. They are then filtered for maximal quality and compressed by MP3, MP4 and similar compression algorithms to save bandwidth. And at your place, the compressed audio and video is decompressed and converted from the digital domain into an analog version by your speaker and monitor. In this course we focus on digital signal processing. Signals, speech, audio and images are first digitized or sampled and next stored in memory for processing. It is important to understand that in this course with x of t we mean a signal with amplitude x at continuous time instance t, for instance measured in seconds. Whereas with x of n we mean the nth sample, the nth value or the nth time index of a time discrete signal with amplitude x. In other words, in digital signals we have lost the notion of time. We have replaced physical time or physical distance by an index into an array. For digital processing, for instance by software, that's not a problem at all. But if you want to convert back the discrete time signal into the analog domain, you must know how many samples you originally had, for instance per second for audio or per centimeter for images. That quantity is called sampling frequency. We will talk more about how to pick the correct sampling frequency in lecture number 3. An input-output relation of a signal processing system is nothing else than a description of how an input signal value, typically called y, at time index n is computed from a bunch of input values x at different time indices, for instance n, n-1 and n-2 as shown here. These are the current input value at time index n and two previous values, previous in time. Simple cases are linear combinations such as the first equation. It is very easy to think of more complicated nonlinear input-output relations, like the second equation, but those are extremely difficult to analyze and we're not going to consider those in this course. In this course we will often use shorthand notation for linear output relations. So the equation at the top is written in shorthand by the one below. And then, if you generalize and take a combination of capital M plus 1 input values, each of which is weighted or pre-multiplied with a factor b of m, then we get the equation at the bottom. Obviously, for the top equation we have m is 2, b0, b1 and b2 are all equal to 1.5. This general equation for linear systems or linear filter is going to be the basis for many topics to be discussed in the coming lectures. For that reason, this is the signal processing equation of the week. If you would digitize a time-continuous signal and then look at the resulting time-discrete signal, you basically get an array of numbers as shown here. In mathematical terms, we see this array of numbers as a sum of weighted unit impulses, also called delta functions. As an example, a unit impulse at time index 2 is formulated as shown here. 0 everywhere except for time index 2, where it has the value 1. If you have an array, for instance, with the values 1, 2, 5 and -1 and 0 elsewhere, then we can formulate that signal as a sum of 4 unit impulses at the proper time indices, weighted by the signal values 1, 2, 5 and -1. For an arbitrary signal, possibly of infinite length, the mathematical formulation then looks like this. By this formulation we have decomposed a signal into an infinite sum of simpler signals, the unit impulses. We will use this idea of unit impulses when introducing the concept of convolution in the next lecture. Another way of decomposing signals is using sinusoidal waveforms. This is going to be important for time-discrete Fourier transforms later in this course. Right now it is enough to understand the concept of a sampled sine or a cosine signal. In the continuous world, the cosine function and graph looks like this. In the discrete world, it looks like this one, which is obviously not a real cosine, but a sampled, time-discrete version of it. The amplitude or the height of the cosine is indicated by the parameter a. The parameter phi determines the phase or position of the cosine relative to n is 0. And the parameter omega represents the digital frequency. Just like the index n does not represent real physical time or distance, omega does not represent the normal frequency in hertz, as you may remember from physics class. We will come back to the properties and the interpretation of digital frequencies in lecture 3. Finally, in describing linear input-output relations, we will use two basic signal processing operations. The first one is delaying the input signal over a certain number of time indices. For instance, if we delay over k, the output signal y at time index n is equal to the input signal x at time index n minus k, as shown here. The second operation is the linear combination of input values delayed over different amounts of time indices. We have already seen examples of that, for instance, in the equation of the week. Based on this introduction, we can now say that signal processing has two important goals. The first goal is to find the optimal number and values of weights b of n, such that the output signal y of n has certain desired properties. For instance, to remove degradations from the input signal or to compress that signal. And secondly, to understand what features a particular signal has in tones or frequency content and how these features are influenced by signal processing operations. Those frequency domain features are often input to all sorts of data analysis and machine learning algorithms. To wrap up, here are two exercises that you should be able to solve with the study materials of this week. First, you need to be able to work with unit impulse signals. So given this signal, you should be able to figure out the signal sample values as well as to make a clear and correct hand-drawn plot of the time-discrete signal. Second, you should be able to compute an output signal based on a given input signal and the input-output relation. Given, for instance, this linear input-output relation, what is the output y of n when the input is given by this x of n? Of course, in many cases, these signals extend from -infinity to +infinity. For the calculations, you are typically expected to compute the output values only for a certain range of n. That's it for this week. We do not have mandatory Python assignments for lecture 1. This will only start after the next lecture. But we do have a number of Python exercises for you to get a bit of practical experience with creating, loading, manipulating and listening to discrete time signals. Please carry out those exercises as they help you to prepare for the upcoming Python assignments. See you soon again. Bye bye!